I am John Sushil, a student under Professor Park Yeong-Do from Dong-Eui University. I would like to start by thanking the KWG's authorities for giving me the opportunity to present my work on flux-driven interfacial engineering, dissimilar metal, lab joining of galvanelaed steel and aluminum alloy, through which the application of flux is extended beyond its general known functions. So as we know, with the positive impact of aluminum alloys on weight reduction, emission control and performance enhancement, steel aluminum joining has evolved to be a crucial part in automotive joining. With the years, various joining technologies have been developed for steel aluminum dissimilar metal joining, wherein the fusion joints possess the challenge of uncontrollable IMC formation due to the steel base metal melting, while mechanical joining raises the concern of increased weight of the joint components. On this context, the introduction of weld bracing technology has been in the spotlight because of its versatility, as it combines two different joining methods. The weld bracing technology, as the name suggests, includes welding, where the welding occurs between the low melting aluminum base metal and the low melting filler metal, while the steel base metal remains unmelted and participates in the joining process through bracing technology. Also, as we all know, the basic fundamental principle of bracing is the capillary flow of filler metal on the substrate, which is termed as wettability. Yes, weld bracing technology also demands sufficient wettability. This means that wettability of steel surface is one of the primary factors that decides the quality of weld braced joints. But considering GA steels, the Fe zinc coating possesses a high melting of 950 degrees Celsius, which is a crucial factor that prevents the direct contact between steel and the filler metal, and hence GA steel shows nearly no wettability. As a result, previous literatures and studies have stated that weld bracing of GA steel to aluminum alloys are nearly impossible. The detailed reasons will be mentioned in the following sections. Nevertheless, the formation of hard and brittle FeAl IMCs are also one of the major known concerns to take care to ensure sound joint integrity. So based on the previously mentioned challenges, the objectives of the study is divided into promoting wettability on GA steel surface via surface tension modification with the help of a reactive flux, and extending the application of flux beyond wettability, that is controlling the interfacial temperature and stabilizing the heat input to promote tailored IMC formation. So the experiment methodology is shown here, starting with the coating analysis and comparisons between GA and GI steels. A reactive flux is then applied to the steel surface, and corresponding surface phenomena were tracked on using high-speed camera and IR temperature tracking technologies. The resulting interfaces were studied using SEM ADS technology. Further, the mechanical properties were evaluated through tensile shear test, and the corresponding fracture surfaces were analyzed. The main materials used in the study are galvanized steels and galvanized steels of 1.2 and 1 mm thickness respectively, and aluminum AA645 base metal of 2 mm thickness. Filler metal used is EF4043, which is a generally used aluminum silicon filler metal in steel aluminum joining, and a commercially available bracing flux of potassium fluoride and potassium chloride components. The process parameters in the studies are divided into two. The first one is a low heat input process, which is the generally known or the widely used short circuit mode, and the next one is the high heat input process, which is the approach that focuses in this work. The wettability was investigated through BOP test, while the microscopic analysis were performed on the lab joints between the steel and aluminum. So moving to the results and discussion section, the first objective of enhancing or promoting wettability on GA steel surfaces. So to begin with the coating analysis, as shown in the Fe distribution comparison between GI and GA steels, the coating layer of GA consists of nearly no Fe, indicating pure zinc availability. Usually it is known that GA steels exhibit superior wettability in bracing, which is mainly attributed to the low melting zinc in the coating. But why? Because the zinc in the coating helps in the prevention of oxides on steel surface. Also, it has the ability to deoxidize the molten droplets during the bracing process, that is in total a cleaning action. Also, the liquid zinc film that forms on the steel surface will act as a carrier to enable the spreading of the molten pool. Whereas GA coating has sufficient amount of Fe in the coating layer, making it as Fe sink phases, namely delta and gamma phases, which has a high melting point of nearly 950 degrees Celsius. Now you can see why Ga has nearly no wetting. Yes, because there is no pure zinc available, unlike the Ga steels, and thus the benefits or advantages of the zinc is not available for Ga steels that prevents or retards the wettability. As a consequence of the coating type on steel surface, a comparison of BOP process window between Ga and Ga is made here. In the Ga process window we can clearly see, even though narrow, there is a small range with sufficient wetting. Beyond this range, the low melting zinc will be vaporized much faster, leading to arc instability and discontinuous metal deposition. Whereas for Ga, there is no possible window for wetting. At low heat inputs, the coating on the steel remains intact and prevents the contact between steel and filler metal. As a result, there is no metal deposition happening. At higher temperatures, even though the coating is removed, it increases or it enhances the rapid diffusion of FeAl at the interface, resulting in thick IMC formation and interface separation due to the brittleness of the IMCs. The BOP cross-sectional images is shown here, where you can clearly see that for the Ga steels, it shows good wetting with the low contact angles and a long braced interface with a controlled interfacial layer thickness less than 5 micrometer. But if you look for the G interface, as I mentioned above, shows higher contact angle, meaning poor wettability, and the interface is completely separated due to the thick IMCs, which is greater than 10 micrometer, and the weld metal was also filled with needle-shaped IMCs. This indicates that the modification process parameters alone will not improve the wettability of the GA steel surfaces. In order to overcome this challenge, the basics of capillary action, as explained in the Dupré equation, is shown here. The work of adhesion, which is controlled by three surface tension components: the surface tension of steel surface tension of liquid, and surface tension between solid and liquid interface, is shown here. So in here, as the WA term increases, the wettability increases. So in order to have a higher WA, either the surface tension of steel or liquid filler should be higher, or the interface surface tension between solid and liquid should be lower. However, surface tension of liquid filler is actually a constant, as the composition of filler metal does not change in the process. So the only components that can be controlled are surface tension of steel and the interfacial surface tension between steel and liquid filler. Here comes the importance of high melting coating or other films, because all the high melting coating, oxide layers or any other films it will act as an additional interface between steel and filler metal, which means it will increase the interfacial surface tension value, that is the gamma SL term. As a result, the work of adhesion term decreases, which indicates a decrease in the wettability. So in order to have a higher or good wettability and to decrease the interfacial surface tension, a reactive flux is applied. But how does a flux reduce the interfacial surface tension? It is shown here. So firstly, the flux prevents the direct heating of the zinc base coating by the arc, which means the zinc will be retained and zinc vaporization will be suppressed, and as a result the arc will be stabilized. Secondly, the fluorides in the flux have the ability to react with the molten droplets and deoxidize the molten droplets, which is mainly the silicon oxides and the aluminum oxides in the aluminum silicon wire, at a temperature range of around 530 to 570 degrees Celsius, based on the equation shown here. Also, as the welding progresses, the steel surface gets exposed to atmosphere due to the removal of coating, which will cause secondary oxidation of steel surface again. So these Fe oxides are high melting layers again, which will reduce the wettability. But the flux has the ability to protect or prevent the steel surface from the atmosphere to prevent the oxide formation. So the schematic representation here shows, without the flux, what are the oxide layers being formed. The first image is the oxide layer formed on the steel surface as the coating gets removed in the welding process. Similarly, as the molten droplet approaches, it is also covered with aluminum silicon oxide. So in total, between the droplet and the steel surface, there is a thick oxide layers, which will increase the interfacial surface tension and hence becomes a globular deposit and no wetting. But with the flux, as the coating gets removed, the flux will protect the steel surface from oxidation, and also flux will react with the oxides of the molten droplet at a lower temperatures, around 530 to 570 degrees Celsius, As a result, all the oxide layers will be cleaned, or the flux performs a cleaning action similar to zinc, which will enhance the wetting by reducing the interfacial surface tension between steel and liquid filler. So as a result of the above explained mechanism, here you may clearly see that with the application of flux, the wettability of the steel surface is remarkably altered or improved, resulting in a sound braced interface with a sufficient leg length and a very low wetting angle of 32 degrees approximately. Further, the effect of flux in improving wettability was analyzed using high-speed camera technology in the BOP configuration. The case of GA without the flux shows discontinuous droplet depositions, as you can see here, big droplets and narrow droplets, while the GA with flux shows a continuous deposition of the filler metal. A detailed breakdown will be shown in the next slide. So here, as shown here, the wetting phenomena was divided by studying into different stages. Firstly, for the case without flux, the high temperature initial plasma are caused the sudden burning and vaporization of the zinc coating, which is marked in the circular white colored region. So the center of this region is now the zinc depleted region, and the outer region has still the remaining zinc. So as a result, you can see that the droplet was deposited on the outer periphery of the coating vaporized region, which also indicates vapor pressure from the vaporized coating. Also, through the outer periphery, it gradually fills up the circular region by the droplet deposition. And while the deposition happens, you can see that the molten droplets are covered with thick silver color oxides, which remains intact throughout the melting process. Whereas for the case with the flux, the initial arc was immediately cut off. This is attributed to the evolution of gaseous products from the low melting flux, which melted prior to the coating. This prevented the burning of coating and retained the zinc enough on the surface. And the droplets are now stable, and it is indicated by the droplets depositing directly onto the center of the arc region. In the following stages, it was clearly seen that even though the droplets were covered with oxides in the first very few milliseconds, it is gradually getting cleared. As you can see, dark shiny colored molten pool is now becoming visible, with the silver colored layers accumulating to the outer periphery of the molten pool, that is into the slag layers. And the molten pool propagation was closely observed, where flux was seen to act as a liquid film just ahead of the molten pool, thus carrying the molten pool for further spreading, while the almost outer periphery was covered with the slag or the residual forms of the flux. So coming to the second objective, the most known and challenging part, that is the IMC formation. So we already know generally IMCs formed in steel aluminum joining are Fe2Al5 and Fe4Al13, which is usually termed as FeAl3 in the old literatures. But all these are aluminum rich IMCs, which are known to have most brittle, while Fe rich IMCs are comparatively softer, as it has more coherency with the steel matrix. But usually in the weld bracing between steel and aluminum, since the low melting aluminum wire and aluminum base metal is able to provide large amount of aluminum atoms to the diffusion, that is the reason why mainly aluminum rich IMCs are being formed. So on behalf of this context, we can see that all the literatures studied till date focused on lowering the heat input through the development of short circuit mode and so on, such that the IMC thicknesses was controlled, but the phases still remain the aluminum rich phases. So based on this, a new strategical approach was employed in this work to improve the Fe diffusion by increasing the heat input. But older literature studies have shown that increasing the heat input will always increase the temperature dependent diffusion of Fe and aluminum, which will result in higher IMC thickness. So a precisely controlled approach of utilizing the effect of flux and combining it with the high heat input is applied here in order to control both IMC thickness and IMC phases mutually. So as shown here, the conventional high heat input welding processes have studied that the thermal energy causes higher diffusion at the steel aluminum interface, leading to very thick IMC formation and causing solidification cracking at the end of the welding. So this led to the developments in the welding process recently with the evolution of low melting short circuit mode, where an intermediate short circuit mode is employed to reduce down the total effective heat input, and thus only a moderate diffusion takes place at the interface, which will lead to controlled or lesser IMC thickness and a good joint. But in this study we explored the conventional high heat input process by combining it with the flux element, where the flux is able to regulate, or flux is employed to regulate the heat at the interface, controlling the heat at the interface. At the same time, the higher heat input will lead to a promoted Fe diffusion. In effect, the final IMC will be having a controlled thickness less than 10 micrometer, and at the same time a new phase which has much lesser aluminum or slightly higher Fe content. So to identify that, firstly the temporal profile comparison between GA and aluminum lap joints with and without fluxes are shown here. So under the same heat input conditions, it is clearly seen that the interface peak temperature of the case with the flux was reduced down to 1000 degrees Celsius compared to the case without the flux, which was around 1500 degrees Celsius. So it is almost a 500 degrees Celsius reduction. This reduction in temperature is attributed to the endothermic decomposition of flux that happens at a range of 400 to 600 degrees Celsius. Also, in the Fe aluminum binary phase diagram, it indicates that the formation of IMCs occur above 600 degrees Celsius. So correlating that data to our temporal profiles, we can see that the total effective time period over which the interface peak temperature remained in the IMC formation range was reduced to almost 6 seconds, which is half compared to that of the case without flux, which was 10 seconds. So in total, higher heat input process with the flux was able to reduce down the interfacial peak temperature and control the IMC formation time duration, which means both diffusion and growth rate was controlled using a flux. So coming to the interfacial analysis, first here it is shown the case of GA steels and aluminum lap joints with the flux at generally used low heat input or short circuit mode. So here the main IMC layers was considered of Fe2Al5 near the steel side and Fe4Al30 to the aluminum base metal side. And Fe2Al5 layers are generally known to have higher residual stresses and higher brittleness, causing easy fracture at the steel side. Compared to the approach presented in this work, that is high heat input with the flux, we can see that the IMC thickness has been increased slightly, even though it is still controlled to less than 10 micrometer. But other than Fe2Al5, now there is a newly layered form which is FeAl2 near the steel matrix. Hence, the easy separation of Fe2Al5 and steel interface will be controlled, which will enhance the joint strength and fracture toughness. The corresponding EDS data is shown here. So with the high heat input and flux approach presented here, we can see that the points which is very close to the steel side or just right above the steel, points 3 and 6, had aluminum weight percentage 50 or less than 50, which is generally in the FeAl2 range. For Fe2Al5 it should be higher than 50, which is shown in here in the conventional short circuit mode process. So the corresponding mechanical property evaluation through tensile shear test showed that both conventional short circuit mode and high heat input work presented in this work showed interfacial failure, with conventional mode having 4.4 peak load, kilonewton peak load, and the new strategy improved the peak load to 5.4 kilonewton. But if we look at the total displacement, it was significantly higher for the newly developed approach and gradually decreasing the load, which indicates the improvement in the fracture toughness with the addition of new FeAl2 layer. To further analyze this, the fracture surfaces were studied and the failure locations were identified. So in the conventional short circuit mode, we can see that on the steel matrix of the fractured samples, there was no IMCs found. Instead, the IMCs were still intact on the weld metal, which means the fracture occurred between the steel and the IMC interface. Whereas for the case presented here, which is high heat input with the flux on the steel matrix, we can see that there was still FeAl2 layer present, and Fe2Al5 layer was mainly found on the welded metal side. This clearly shows a change in the fracture location from steel IMC interface to IMC interface between the Fe2Al5 and FeAl2, which also indicates the improved coherency of FeAl2 layer with the steel matrix and the improved fracture toughness. So to conclude the results of this work, the application of reaction flux promoted the wetting on GA steel surfaces which otherwise has zero wettability. This is attributed to the protection of zinc by the flux, the cleaning action of flux on molten droplets, and the shielding effect on the steel to prevent secondary oxidation of the steel surface. Also, the endothermic decomposition of the flux absorbs heat by almost 500 degrees Celsius, which in turn stabilizes the interfacial temperature and control the growth rate of the IMCs. Also, the control of the interfacial peak temperature resulted in promoted Fe diffusion with the higher heat input, which finally resulted in the formation of aluminium lean or Fe-rich IMC, which is the FeAl2 layer, which is usually not reported in the previous studies. So thank you for your time and attention.